All right, so I want to start the lesson today with the course with this the Blackboard site for Math 182 because we are talking about section 5.9. Section 5.9 deals with approximate integration, and as we discussed, there are integrals that we cannot find explicit antiderivatives for. And that means, like, if we want to compute like a definite integral and we can't find the antiderivative, our main alternative, our only alternative really, is to use numerical techniques to approximate the integral. And last time in our last class, we talked in section 5.9 about some of the different rules that are used to approximate these definite integrals, namely the left endpoint rule, the right endpoint rule, the midpoint rule, the trapezoidal rule, and Simpson's rule. And in your, well, yes, and so let's see. So we know we can approximate these definite integrals with these different approximations, these different rules. The question, though, then is how accurate is the rule? Can we have an idea of how accurate the rule is? And it might seem a little odd because that we can actually get a bound on the error of our approximation to the definite integral, because normally when you want to compute an error, you take the difference between the actual value and the approximate value. But so when we find a bound on an error of our approximation, it isn't the actual error. It's just you're just saying the error can't be any greater than this amount. And there are formulas for those error bounds as well. And if we go into course content, okay, so for instance, the midpoint rule, trapezoidal rule, and Simpson's rule all have error bound formulas. And if you go into course content here, okay, let me make it a little smaller here. Yeah, if you go into the course content and click on the here link, okay, the course content displays all the recordings of our lectures. If you go down to section 5.9, approximate integration, then there is a link here for table of numerical integration formulas. Okay, so that and that table, perhaps, well, that table basically combines the midpoint, trapezoidal, and Simpson rules along with the error bounds, error bound formulas. Let me just see one moment. Let me find that document. Maybe I will upload that as well and show it to you real quick. Give me just a moment here. Okay, one moment, class. Okay, I'm uploading it. How many have clicked on the link, the table of numerical integration formulas, and see the handout there? Good. All right. Excellent. 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 And I actually made that handout just because I think it'll make your life a little easier. All right. So hold on here. Now let me see. Where is this? There it is. Okay. So let's share that. Yeah, here's the formula sheet. Okay, so trapezoidal rule, midpoint rule, Simpson's rule, the formulas are all there. And then you have these error bounds for trapezoidal rule, midpoint rule, and Simpson's rule. Now, this formula sheet you will have access to on your exam next week. You will have access to that formula sheet. You do not have to memorize these formulas. from section 5.9. So you'll notice that if we look at the error bound, so like for instance, the error bound for the trapezoidal rule, what this says is that the error, if in approximating a definite integral, that's e sub t, well, that's the error e. The error in approximating a definite integral using the trapezoidal rule, and I should really say the absolute value of the error. An error, we don't care if it's positive or negative. We just care about, how far or how much are we off. So the absolute value of the error using the trapezoidal rule in approximating a definite integral is less than or equal to this right-hand side. And it says big K times b minus a cubed over 12n squared. So a and b are your lower and upper limits of the integral. And the K value is determined using this criteria. What you do is you take the second derivative of the function. The function would be like, okay, you have an integral from a to b of f of x dx. This is the function they're talking about, okay? And this function here, you would take its second derivative, and then over your interval from a to b, over this interval here, you would determine where's the second derivative of that function the largest, like how large can it get, and then you pick the largest value of the second derivative and set it equal to k, because k is greater than or equal to the absolute value of that second derivative. And so that's how you find k. And we'll certainly do an example. Are there any questions on that, at least so far? Okay. Well, so we have these different error bounds, and when you look at the, if we look at the three error bounds here, for trapezoidal rule, midpoint rule, and Simpson's rule, and remember, you can zoom on the right. You have a zoom button if you want to make it larger. But when we look at these three rules, which rule seems to have the smallest error bound? I mean, trapezoidal, mid, and we can't always say that it would always be the smallest, but in general, looking at what I'm trying to say is, in general, looking at the error bound for the trapezoidal rule, okay, that's the first one, right? The midpoint rule, that's the second one. And Simpson's rule. Which error bound seems to be maybe the best, the smallest? What do you think, Samuel?
Error bound for trapezoidal.
Well, so for the trapezoidal, and this is, well, let me ask you this. What, if we focus on the denominator, if we focus on the, so I want this, if we focus on the denominators, let's do that for a moment, one moment. Okay. If we look at the denominators, and Nathan thinks it could be Simpson's, which denominator, and n, by the way, is the number of subintervals. So you can see that Simpson's rule, and Leping and Nathan, Simpson's rule has the largest denominator. So that's going to tend to make the error bound smaller, because you're dividing the numerator by a greater number. So it isn't always the case, but more often than not, it is the case. And the reason for that is Simpson's rule in general approximates curves better, functions better than the other two rules. So remember, if you remember, let me just see here. Hold on. Maybe let me bring up the ebook real quick. One moment, class. It's worth doing, but I got to bring up the ebook. Let's see here, chapter. Yeah, okay, one moment, class. Hold on here. Okay, so there's the approximate integration section in 5.9. And I don't know why it's doing that. Hold on. Okay. And like here in figure 1, you can see, I mean, we're focusing now on the midpoint rule, which in figure 1 is the third picture. Okay, so there you're trying to approximate the area under a function, under a curve, and you divide the distance from A to B into subintervals. And every subinterval, you pick the midpoint to determine the height of that rectangle. That's the midpoint rule. And then and this is really review. We talked about this in the last lesson. Trapezoidal rule. Here's a picture of trapezoidal rule. There, you are using trapezoids along every subinterval. So you know that's good. And you know the error comes in. Well, I want to say this the right way. So like, okay, let me just comment here real quick. You know, just drawing a function here. So like for the trapezoidal rule, okay, the error comes here, right? In other words, this gap here, the trapezoidal rule, this trapezoid, the area of the trapezoid is missing this area here under the curve. So the error due to the approximation is due to the fact that these, like the trapezoids or rectangles, they don't approximate the function perfectly. Okay, but and that's true. That's just true. But for Simpson's rule, you're not using like line segments to approximate the function. Okay, you're using parabolas in Simpson's rule, and parabolas tend to because they're curved in nature, they will tend to approximate a function that's curved in nature better than like Simpson's rule or trapezoidal rule. And so for that reason, if I go back to the formula sheet here, for that reason, you notice that the denominator in Simpson's rule is quite a bit larger than that in the midpoint rule or the trapezoidal rule. So, you know, depending on the function, usually Simpson's rule is the best, not always, but generally, usually Simpson's rule works the best because of the large denominator in the bottom. That'll make the error bound small because you're dividing the error bound, the bound on the error, which is given here, you're dividing by a bigger number on the bottom. So that helps make the error bound smaller. Does that make sense? Are there any questions on that? Samuel, how do you feel about that? Are you comfortable?
Yes.
All right, excellent, excellent. Okay, well that being said, we need to look at some problems where we apply these error bound formulas. So let's go ahead. Let me bring up an example here. Okay. So here's an example of an integral that you cannot determine this integral exactly. Like if I want to say this right. So like if you had the integral from 1 to 2 of e to the x dx, well, you could determine that integral exactly, right? You could get the area under that curve and get an exact number. But in our problem here, you have e to the power 1 over x, and there's no antiderivative for that function. There's no antiderivative for e to the 1 over x power. So we're going to have to use approximations, and what we're going to do here, and I'll let you copy this down, we're going to do a midpoint rule approximation based on 10 subintervals for this integral. And then we're going to estimate the error of the approximation. We're going to estimate the error using the appropriate error-bound formula. Okay. All right, so let me give you a moment to copy this example down, and then we'll move forward here. Okay, so let's see here. Now, so we have limits from 1 to 10. Okay, limits from 1 to 10. Oh, sorry, 1 to 2. Sorry. So here's 1, and here's 2. Hold on here. Okay, let me make that a little bit nicer. Getting better with this eraser. So what would delta x equal? Okay, you have your formula sheet, and you could download that formula sheet, right? You could download that. You should download that formula sheet. What would it be, Samuel?
It would be 2 minus 1 over 10.
That's right. Good. A minus B, or B minus A, I should say, over 10. So that's going to give us 1/10. So in the formula, we have to pick values. So what would the, what's the, let's see, 1, well, how many subintervals are there? Oh, there are 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Let me see here. Hold on, everybody. So how many subintervals? Well, there are 10 subintervals, and what's the first number going to be here? What's the first number going to be there?
1.1.
1.1. That's right. Good, Nathan. Now, for the midpoint rule, what do we have to do for this first interval? The value that we're going to be using is halfway between 1 and 1.1. That halfway value would be what? What's halfway between 1 and 1.1?
1.05.
1.05. Okay, and then the next value would be 1.2. Okay, and then the midpoint between 1.1 and 1.2 would be what?
1.15.
1.15. And so forth. Good. And incidentally, we call the 1.05, that's denoted in the midpoint rule by x1 bar. And 1.15, your next value would be the second value would be x2 bar. Okay, and so you just have to find your 10 midpoints. They're 10 intervals, so they're 10 midpoints. And let me show you on the next page then. Here, well, no, that's okay, that's the formula sheet. Okay, there's the midpoint rule. That's what we're using. Okay, so here we are. Okay, so I really wrote it out nice for you, so you could see it. And what we're doing, of course, is we're utilizing the formula. Now I know, for instance, like the TI calculator, I know there's a formula that can compute these approximations. You know, I'm not going to be secretive about it. But the problem is you won't learn how to apply these approximations if the calculator does it for you. So what I want you to do is work it out like I'm showing you here, where you actually, you know, show the steps where here's the midpoint rule. And then here I'm plugging in the values into the function. And then the next step is I'm gonna, write out all the values, all the function values. Okay, so it is time consuming, and you might notice in the homework I don't give too many problems because it does take time to do. But still, to really learn it, you have to go through the process of just working it out, and and like I'm doing here. Are there any questions on this? All right, well, so our function, of course, is e to the 1 over x power. And so, like the first function value, f of 1.05, would be e to the power 1 over 1.05, right? And then the second function value would be e to the power of 1 over 1.15. So I would expect to see this kind of work on your exam next week. That's called showing work. But once you've shown your work, now you could plug all these values. You could substitute all of these, compute all of these values, all of these function values using like a TI calculator or using Desmos. And if you do, you would get this value right here. And this is to the, what, 8th decimal place? So the integral from 1 to 2 of e to the 1 over x power dx is going to be approximately, it's approximately equal to this value, 2.019101885. Are there any questions up to here? All right. Well, so this is nice. We have an approximation of our definite integral. We have an approximate value, but one can ask the question, how accurate is this approximation? Could we get an idea of the accuracy of this approximation? What's the most that approximation could be off? And for that, then we're going to have to use our error-bound formula for the midpoint rule. Okay, so may I move to the next page? Okay, Nicole's feeling good. Laping's good. Ryan's good. Audra's good. All right, very good, very good. Thank you. Josie's good. So all right. So now I'm going to go and use this formula here. That's the formula I want. So Do I know in this formula what b is? What's b equal to?
2.
That's right, Samuel.
Oops, wrong.
What's a equal to?
1.
1. Good. Your upper and lower limits. What's n equal to?
10.
That's right, Maria. Because we're midpoint rule approximation with 10 subintervals. What's the only thing left to find?
K.
K. Okay, so we're going to find K. Okay, now in the formula, it says, let me go back here actually. In the formula, it says that K is greater than or equal to the absolute value of the second derivative of our function. Okay, so we got to find the second derivative of our function. So I will go then here. I wrote down the error-bound formula here. I wrote the error-bound down. But, of course, we have to find K. Okay, and so, and I know you need to copy this. This is our function. Here's the first derivative. And then we go get the second derivative. Let me let you catch up here a little bit. And please ask me if you have any questions, okay? Okay, now when when I compute the first derivative here, I have e to the x, e raised to the power x to the negative first, because 1 over x is x to the negative first, times negative x to the negative second. So what rule did I use here to compute that first derivative?
Chain rule.
That's right, Samuel, the chain rule. That's right. Okay. And then to compute the second derivative, well, what rule am I using here?
Product.
The product rule. That's right, Nathan. So the negative sign, I just bring the negative, out front here. And then I have the derivative of this product. And so this is like, well, yeah. And then what I want to do is I want to write the second derivative in a nicer form. So of course, I simplify my second derivative here. X to the negative second times negative x to the negative second is negative x to the negative fourth, but the negative gets multiplied by that negative, and you end up with this. I'm going to factor out the common factor of e to the power x to the negative first. Just rewrite the second derivative in a nice form. because I got to analyze this second derivative. I have to analyze it. I have to try to determine over the interval from 1 to 2 where this second derivative is greatest. Okay, so because I have to find my k value, and the k value that I find by the formula, and that formula comes from numerical analysis. I took a whole year of numerical analysis, whole year class on it, and I remember approving that formula in the class, or seeing the proof of it in the class. But we have to find k. So we have to know, and this is over the interval from 1 to 2, by the way. Okay, so let's find k. May I go to the next page? Are there any questions? All right, all right. To the next page then. So again, here's our second derivative. And when x is between 1 and 2, and that's of course the interval, you know, our integral goes from 1 to 2. The absolute value of the second derivative is just equal to the second derivative, because this second derivative is positive. It's always positive when x goes from 1 to 2. So we can drop the absolute value, and but we note that that this function is a decreasing function. Now, how do we know that? How do we know that? Well, this function here, we could graph it on our calculator, for instance. We could graph it on our calculator, and we can see that it's a decreasing function. But you could also sort of prove it to yourself. The exponential function here, as x gets larger, that exponential function gets smaller. And then this rational function, too, is going to get smaller with x. As x gets larger, that x to the fourth on the bottom, it dominates, you know, and that gets big, making that function smaller. So it's a decreasing function. And for most of the problems you're going to deal with, well, I got to be a little careful. Certainly some of them, you'll have either an increasing or a decreasing function. So I mean, let's just sort of draw a little diagram to help us now. If I have okay, if I have a function, maybe I'll put it in blue. Well, this is x, this is y, and let's say I have a function and well, hold on. I'm going to just draw a decreasing function, and actually, let me just do one thing. I want to plot this second derivative on my calculator, and just to see what it looks like. Just give me a moment on that. It's not takes a little work to type it in, but that's okay. I'm just graphing it on my calculator here. Now hold on. Yeah. So this is actually a concave up function, and it decreases this way. This is accurate. So if I wanted to just draw a little sketch of my second derivative from 1 to 2, okay, this is indeed what it would look like. You can graph it on your calculator. You can graph it on maybe Desmos. How many graph functions on Desmos sometimes? Okay, Lepine does, and so I've heard it's pretty popular, so that's why I mention it. And it's free too, right? It's free. So the college tries to promote Desmos because then students don't have to buy the calculator. But I still think it's worth getting, but you know what I mean. All right, so there's the second derivative, okay, or the absolute value of the second derivative, but it's the same as the second derivative. So, okay, it's a decreasing function. Where is this function? Where is this function maximized? So if you have to look at between 1 and 2, all the x values, you know, this whole interval here, what x value is the function maximized at? At 1. That's right, Abadar. So that's why we say here below that the second derivative is maximized at x equals 1. And therefore, k, okay, k is going to equal the second derivative when x equals 1. So, I mean, is everybody seeing this okay? The second derivative takes on its highest value right here, right? So the second derivative, let me just get this, this is fine, but let me just take a little bit of that off. The second derivative is maximized when at x equals 1. And so hence k is going to equal the second derivative of f at x equals 1, and that's going to turn out to equal 3e. And WebAssign will want the exact value, okay? Does not want a decimal. If you can get the exact value, it wants the exact value.
So
Are there any questions?
I have a question.
Yeah.
So if perchance the function was maximized at 2, then you would evaluate that second derivative at 2, correct?
That's correct.
Okay, thank you.
That's correct, Maria. And so in that case, we would have an increasing function in that, or an increasing second derivative, I should say. And the maximum would be at 2. That's right. That's right. Very good. Very good. But of course, our second derivative is decreasing. So, okay. So we want the bound on our error to be as small as possible. So you know, k. I mean, I want to say this the right way. So k here is greater than or equal to 3 times e. So pick k to be as small as possible. Let k equal 3e, and now you're able to compute your error bound. So the bound on your error, okay, the absolute value of your error, so the approximating our integral using the midpoint rule, we get an approximation, okay, and the midpoint rule of approximation based on 10 subintervals, the difference between that approximation and the true value of the integral, which no one will ever know, that error is assured to be less than or equal to e over 800, which as a decimal is 0.0003398. And therefore, the error of our midpoint rule approximation based on 10 subintervals are the error of our approximation to the true value is less than 0.0003398. Okay, so it's about 3/10,000ths roughly, the bound on the error. So we can be assured that our approximation is accurate to the true value of this integral to about 3/10,000ths. Okay, and so the question is, are we happy with that? You know, so if we're doing computations, is this approximation good enough based on that error bound? You see, you can't really know how good the approximation is till you see the error bound. Yeah, Samuel, question?
Yeah. What is this right here?
Oh, what that is I wanted you to, so that this is not abstract, what does this mean here, the absolute value of the error? That means, well, the error is the difference between the approximation and the integral itself. The difference between the approximation and the integral itself is your error. The error is the difference between the truth, which is the integral, and the approximation, which is the midpoint rule. Does that make good sense?
It's just what the absolute value of en is.
It's the error is the absolute value of the difference between the midpoint rule and the integral.
Thank you.
All right, very good, very good. I mean, I don't want this to be abstract, and that's why I'm, putting it in there. And so, good question. So let me ask you, how could we get, like, if we wanted a better approximation, if we're not happy with an error bound of roughly 3/10,000ths or 33, well, it's about 3/400,000ths, right, based on our error bound here. What can we do to get a better error bound?
Increase the number of intervals.
That's right, Maria. Good. We can increase the number of subintervals. Now, of course, the cost is that it's more work than to get the approximation. It's more work because you have more function values to compute. But that's the way it is. That's the way it is. I shouldn't say that always, but in this case, yes. Okay, and another way too is you could use like the Simpson's rule approximation and maybe get a better result. Okay, so now we'd also like to determine if our midpoint rule approximation is an underestimate or an overestimate. Okay, so I'd like to show you that on the next page. In your homework, you have problems where they ask that, and usually they're multiple choice. You might have like one chance to get it right. Sometimes I got to be careful, maybe two. You can look and see how many chances you have, but usually I guess it would just be one, right? Either it's an underestimate or an overestimate. So how would we determine if our midpoint approximation is an underestimate or an overestimate? What might be very nice to have? to help us picture this. What do we need? It's worth 1,000 words.
A picture.
The graph.
Picture, graph. Good. And so I'll go to the next page, if everybody's good here, and show you a picture. Okay. So the graph of e to the 1 over x power, or e to the power 1 over x, I should say, it's concave up. And what I've done here is I've graphed. Well, I want to be a little careful here. The graph, if you graph this function, you're going to see it looks concave up, and it is concave up. And so, okay, does that mean midpoint rule approximates, or the midpoint rule approximation, is it an underestimate or overestimate? Well, what I do is I just draw a picture of some concave function, and I draw, like, as an example, a subinterval, and then I pick the midpoint of the subinterval, and then of course that value, the function value, this isn't my function here, hold on. Right, this is my function, my concave up function. So the midpoint of the interval determines the height of the rectangle. And if I were to draw other rectangles, the behavior would be similar to what you're seeing here. Basically, I draw the rectangle, and I say to myself, okay, well, there's like when I'm trying to approximate the area underneath the function. So there's area here that I don't want. That's gained area. And then over here, there's area that I didn't capture. That's lost area. So based on the fact that the function is concave up, is the area lost more or less than the area gained?
Can you repeat the question?
Sure. Is the area that's been lost here, okay, this red area I'm sorry, the area gained, the red area, is that more or less than the area that was lost, the blue area? What do you think based on the picture?
Less?
It's less. That's right. So that means then that the area gained is less than the area lost. So the net gain is the net I want to say it's the right way. So does the midpoint rule then over-approximate? Is it an overestimate or an underestimate?
Underestimate?
It's an underestimate, because even though we gained area here, we lost area too, using this approximation, and so it's an underestimate. And it would be the same for every rectangle. Yes, Tal.
Regarding this, are we supposed to do this for every situation like this that we have? Are we just supposed to eyeball it, or?
Well, you are intuitive based on the picture. Intuitively, I hope you can see that it has to be true. Let me ask you this. Let me do something different a little bit here. Hold on. All right. Let me draw a line here. Hold on. So, you know, we're done with this. Midpoint rule is an underestimate because the function's concave up. Let's say, well, let me go to the whiteboard. I want to go to the whiteboard, but who's still copying this down? Is everybody good? Tal asked a very good question. All right, let me go to the whiteboard for a moment. And, man, a lot of buttons to click, but that's all right. We'll get there. Okay, let's say that instead of a concave up function, let's say you had a concave down function. Okay, concave down. And what I'm going to do is, let's say we're dealing with the midpoint rule. Hold on here. Got to be a little careful. Man alive. I gotta click on so many buttons, you know, to get this, but that's all right. Okay, so I'm just drawing something here. So, you know, here I have one subinterval, and then this is the midpoint right here. The midpoint determines the height of the rectangle. And this yellow area here. Now, is that yellow area included in the approximation for the midpoint rule? Is that included?
Yes.
Yes.
It is. It's in the rectangle. It's in the area of the rectangle. Okay. Do we want that area?
No.
No.
No, we don't want this area, but we're getting it anyway, right? So this is area gained. That's area gained. All right, in the approximation. Now let's look at this purple area here. Okay. Hold on here. One moment. Hold on. Is this area lost area or gained area?
Loss.
That's lost area. Okay. And this would be true for any concave function. Any rectangle, if I were to draw another rectangle, you know, if I were to draw a, you know, a second rectangle here, same situation. Same situation. So I only really need, if I can learn something about one rectangle, that's all I need. Now let me see here. Okay, so is the area gained? Okay, and I might have to, hold on. I'm going to edit my picture a little bit, everybody. That's okay. Hold on. Okay, so is the area gained smaller or greater than the area lost? Is the yellow area, the area gained, smaller or greater than the purple area here, the area lost? It's close, but if you had to say, what would you say? The area gained is, hold on. All right, I gotta get you to, there we, yeah, greater's what I'm looking for, okay? Yeah, I'm drawing it, you know, by hand here on the board, but the point is, with a concave down function, this is concave down, CD, right? Concave down, our function's concave down. So concave down function, using the midpoint rule, the gained areas for all the rectangles are going to have more area than the lost areas for all the rectangles. So is the net gain positive or negative?
Positive.
Positive. That's right, Sophie. The gained areas that are in the approximation are greater than the lost areas that we want in the approximation. But the net gain is positive. And so in this case, for a concave down function, CD, concave down, would the midpoint rule be an overestimate or an underestimate?
Overestimate.
Overestimate.
Will
That's
it
what I'm
always
getting.
be an overestimate for
It'll
a
always be an
concave down
overestimate.
function?
I'm sorry?
Will a concave down function always be an overestimate for the midpoint rule?
Yes, it will. Yes,
And
it
it's
will.
so then for a concave up, it will always be an underestimate.
That's correct, Maria. That's right. And then we can ask the same question for other approximations, like, for instance, the trapezoidal rule, you know, or the left endpoint rule, or the right endpoint rule. And to figure that out, you have to, you know, draw a little sketch and hopefully intuitively get comfortable. Tal, are you all right with that?
Yeah, I think so.
You're more comfortable. Okay, good. Okay. Well, on that note, let me go to a new example now.
Are there situations where the area gained equals the area lost or no?
There are situations where the area gain can equal area loss. There are, Sophie.
Okay.
Really, but I think in your homework, most of the time, I don't think you're going to have that kind of situation. I don't believe. But sure, there are times, like if you had if your function were a line, for instance.
Mhm. Yeah.
You know, if the function were a line, then yeah, in that kind of situation. It's more interesting though when the function's like curved, isn't it?
Alrighty, thank you.
Okay, you're welcome. You're welcome. All right, so let's go ahead here and continue on here. So, okay. Well, let's stick with this integral. Let's stick with this integral here. And let's ask ourselves how many subintervals would be needed to guarantee that the midpoint rule approximation for this integral would be accurate to within 1/10,000th. When we had 10 subintervals, the error bound for the midpoint rule said that we're guaranteed that our approximation would be accurate to within about 3/10,000ths. But now we want a tighter error bound, a tighter bound on the error. So naturally, that means we're going to have to, would we have to increase the number of subintervals or lower the number of subintervals if we want a tighter bound on the error of our approximation?
Increase.
We have
Increase.
to increase. That's right. That's right. So let me give you a moment to copy this example down, and then we'll proceed forward. If you have any questions, let me know. Yes, Samuel.
Why is it increased?
Well, when n equals 10, when n was equal to 10, and we're using the midpoint rule based on 10 subintervals, the error bound for the midpoint rule, based on the last example we did, was less than or equal to 0.0003398. Okay, that was the bound on the error.
Wait, so if n increases, that means the denominator increases and the number gets smaller?
Well, the denominator would increase the error bound, but you see, because we want a smaller error, yeah, that's exactly right, basically. Yeah, that's right what you're saying. That's very good. To get a lower error bound,
Okay.
we need to increase n, because the denominator would get bigger, and then that would make the error bound smaller. Excellent, excellent. Okay, so we're going to use the error bound formula. We already know what k is. K is equal to 3e. We computed that in in the previous example. It's the same function here, e to the 1 over x power, or e to the power 1 over x. Okay, so let's move forward here if we're good. All right, what we're requiring is that the error for the midpoint rule approximation be less than 1/10,000th. So we can assure that if we set our error bound to be less than or equal to 1/10,000th. So remember, in the error bound, k is equal to 3e, and of course the denominator is that 24n squared. And then you have the b minus a to the third power. That's this part here. It's the same integral, b equals 2, a equals 1. So what we have to do is we have to solve this inequality for n. So that means 3e over 24n squared is less than or equal to 1/10,000th. And what I'm going to do is I'm going to multiply both sides of the inequality by 24n squared. Then you get simplification here on the left, and then you get this inequality here. How many of you have been a while since you've solved an inequality before? You learned about them, right? When you were younger, and you know, here, hey, here's an example of one, right? So I have to solve this for n. So n squared would be greater than or equal to 3e divided by the 1/10,000th times 24, and I'm going to take the square root of both sides so that I can get an n. And so it turns out n is greater than or equal to 58.29. Incidentally, when I divided here, you know, I divided both sides, right, by the by 0.0001 or 0.0001 times 24, right? So cool. This material. I thought, though, when I divided an inequality by a number, I thought sometimes I had to worry about the inequality switching signs. But the inequality didn't switch signs here, right? The inequality stayed less than or equal to. Why didn't the inequality switch signs?
You weren't dividing by a negative.
That's right. Good, Maria. I'm dividing by a positive. This, you know, whatever value this is, 0.0001 times 24, it's a positive value. So end up, you know, the inequality doesn't switch. Now, n is greater than or equal to 58.29. Are there any questions so far? All right, so can I have 58.29 intervals?
No.
Can't have that. So, well, all right, so am I going to use, is it okay to use 58 intervals? I mean, if I
No,
round
it has to be
58,
59.
it has to be 59. So even though 58, subintervals have to be an integer, the number of subintervals you use. So 58 is, if you round 58.29, you'll get 58, but you don't want to do that because subintervals, if you need at least 58.29 for n, that means you're going to use 59 subintervals. And so on the next page, then, we need 59 subintervals to achieve the accuracy we want. And you know what's interesting is the 1/10,000th is basically, well, let's see here. You're basically bringing your, I mean, we had basically 3/10, when we had 10 subintervals for the midpoint rule approximation, the error bound was about 3/10,000ths. If we want to get the error bound down to 1/10,000th, uh, which is by like a factor of 3, we need to increase our subintervals by about 50 subintervals. N equals 10 subintervals to N equals 59 subintervals. That's about 50 more intervals that you have to do. So you see, you get a more accuracy, but the price is you have to do more computing. And of course, if we were like, programming a computer to do this, you would be using more computing time. So it's really important sometimes to ask, how much accuracy do I need for my approximation? Because you see, if we ask that question first, how much accuracy do I need for my approximation, and we determine the number of subintervals, that could be, then that determines computing time. Now, 59 intervals won't take long to do if we program this in a computer using like C or something like that. But you might determine, if you're doing like an astronomical application, something with astronomy, you might determine that you need maybe this many subintervals. How many subintervals is that? 6 zeros gives you a million. 9 zeros gives you
Billion.
a billion. Okay, so you might that might be a very important question for a computer scientist to find out, so that they can determine how long the computing time is going to be. How many are computer science majors here? Okay, Jazi is, and Abidara, and Samuel. Okay, so you can see this is a naturally good question. Okay, let's do another example here, and then we'll be able to take a little break. Let's do another example. Okay, I want to have another example where we're going to be using the error-bound formula. So I'll give you a few moments to copy this example down. Okay, so again, we're presented here with an integral that there's no explicit solution. I don't think you can find this in the table of integrals. I don't think, let me just see here. One moment. Yeah, I don't think that's in the table of integrals at all. You know, I don't think so. So we want to approximate this integral, but before I try to figure out, before I do a trapezoidal rule approximation, you know, I want to determine how many subintervals would guarantee that I would have, that my trapezoidal rule approximation would be accurate to within 1/10,000th. Okay, I mean, to me, that's a more important question to ask before doing the trapezoidal rule approximation. So, okay. All right, well, then what we have to do here, let me just go back here to the formula sheet. Here's that formula sheet. It's under content area. If you go to the content area in Blackboard, just a reminder, and click on that Chapter 5 here link, it'll take you to Chapter 5 content, and there is a link that will allow you to download this handout I made. It's for section 5.9. Look in section 5.9 under content. So okay, we got our trapezoidal rule. There it is, and there's the error bound. Oh my goodness, what do we need to find? What do we need to find? We know B, we know A. Samuel?
F double prime.
I'm sorry?
F double prime.
That's right, because we got to determine that our big K value. Okay, so all right, let's move forward here then. Sorry, let me just, here we are. So this is our function. This is our function. One moment, let me just check one thing here. I hope you're having a good time. I'm having a good time. I like this material a lot. But hold on here. How many of you are having a good time? I guess. Okay, thank you, Nicole. Thank you. Now, you know, the function is 5 times the cosine of x squared. I could bring that 5 out in front of the integral, you know, but I would have to bring it in later, you know, so I think it's just better to leave it in. Okay, so here's the function. Well, I understand, Samuel. It is harder than what you've seen. You know, but hopefully with practice you'll feel, you know, everybody needs some practice with it, sure. Here's the function, 5 times the cosine of x squared. Here's the first derivative, f prime of x. And what rule did I use here? What rule did I use to get the derivative that you learned in Calculus 1?
The chain rule.
Chain rule, right. The outer function is the cosine. The derivative of the cosine is minus sine. And then the inner function is x squared. So the derivative of x squared is 2x. So, okay. And then we get f prime of x equals negative 10x times the sine of x squared. And now we have to compute the second derivative. So, of course, product rule and chain rule used at the same time. And I end up writing my second derivative this way. I factor that negative out. Now my interval's from 0 to 1. Okay, my interval's from 0 to 1. So every one of these functions inside the parentheses is positive from 0 to 1. Okay, and that's important because that just means then that I still have this negative here, right? I still have that negative, but the absolute value of that second derivative then is just going to equal 10 times the sine of x squared plus 20x squared cosine of x squared. Okay, because when I take the absolute value of my second derivative, that removes the negative sign, makes it positive. And what's in the parentheses here, what's in the parentheses, what's in the parentheses here is already positive. So this makes sense. Please let me know if you have any questions.
Professor, can you say again why this 3 is great 0?
Why, like the 10 times the sine of x squared is greater than 0?
Uh-huh.
I looked at a graph. I looked at a graph of it, but I don't really need to. Think about the okay, that's a very good question. Let's think about the you know, man, hold on.
Oh, okay. Okay, I think I understand. It's between 0 to 1, yeah.
Right, and if you look at the in the quadrants here, the sine function is positive in the first quadrant. Sine function is positive, and in terms of like x, well, yeah, I mean just graph. Well, I got to be a little careful here how I say this. I'm not saying it the way I want to say it.
I get it. I get it.
Okay? The easiest thing is to draw a graph of the sine of x squared, and you'll see it. Okay, so now what's the next step? I have my second derivative, my absolute value of my second derivative, I should say. What do I need to find now? I mean, what's the point of finding the second derivative? What's the whole point of that?
To solve
What do
for
I need
k.
to find? I have to find that k value. Remember, for the trapezoidal rule, k is greater than or equal to the absolute value of the second derivative. Now, here's the thing. If we were to plot this second derivative, well, hold on here. Let me just actually, I'm gonna plot it on my calculator real quick. So 10 times the sine of x squared, got to make sure my calculator's in radian mode too. 10 times the sine of x squared plus 20 times x squared times the cosine of x squared. Okay, my window's from 0 to 1 on the x-axis. Okay, hold on, sorry. Let me just, one moment. Yeah, so this function is, it's not like a strictly increasing or decreasing function. It's not. Hold on here. Got to be a little careful here. Well, actually, it looks like it's increasing to me. It actually does look like it's increasing. But here's what I want to tell you. Here's what I want to tell you. Like like if we were to say, okay, this second derivative increases from 0 to 1. Well, hold on now. Hold on. Yeah, it does increase. It does increase. I'm looking at this. How many of you are seeing that on your calculator also? How many are graphing the second derivative? Are you seeing that, Samuel? Oh, wait, hold on. No, my calculator wasn't in radians. Hold on. Scratch that, everybody. Yeah, so the second derivative, according to my graph of the second derivative, I'd like to try to draw it here. I think it's always good to have a picture. Okay, second derivative, at least on my graph, looks something like this. Here's x equals, it looks something like this. So I guess it is increasing, right? I guess it looks like it is increasing. So what x would we use?
0.
Well,
Because that's
if
the local
this,
minimum.
1.
That's not local minimum. That's the minimum.
here's a graph of the second derivative, or the absolute value of the second derivative, right here. We want to know where that second derivative is maximized. It's an increasing function. So what x value is the second derivative maximized at?
1.
1.
1. So, okay. So, all right, there we go. We're going to let x equals 1. And so, but here's the thing. We do let x equals 1. Okay. I'm not saying this the way I want to say it. If I let x equals 1, let me put in a step here. I'm not saying this the way I want to say it, actually. Hold on. Okay, so let me get my stylus out here. Hold on. Let me explain here what I'm doing here. Okay, the absolute value of the second derivative evaluated at 1 is 10 times the sine of 1 squared plus 20 times 1 squared times the cosine of 1 squared, right? And you would think then that, hold on here, a lot of clicking. Come on, give me the white color, please. You would think that whatever value that is, what should that equal? What should we set that equal to? 10 times the sine of 1 squared plus 20 times 1 squared times cosine of 1 squared, being that the second derivative is maximized there, we would set that, whatever that value is, equal to what letter?
N.
What are we trying to find? What are we trying to find?
K.
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 So strictly speaking, and I appreciate all responses. You're learning. Everybody's learning here. Strictly speaking, K is equal to this value, because that second derivative, the absolute value of the second derivative, is increasing from 0 to 1. But WebAssign will not accept that value for K, because you have here, like the sine of 1 squared is not a nice value. The cosine of 1 squared is not a nice value. WebAssign wants a nice value. So what you have to do is you have to say this. The sine of x squared at most would equal 1. The cosine of x squared at most would equal 1. So the absolute value of my second derivative would therefore be less than or equal to 10 times 1 plus 20 times 1 squared times 1, which is 30. And that's the value of K that you're going to use. They want the K value to be easy to find. Okay, they want it to be easy. They want it to be a nice kind of pretty value. So whenever you see a sine or a cosine, and you're of any function, and you're doing your limit, your boundary, you're doing you're finding your K value, just replace sine and cosine values with 1. Okay, that's like the rule. And WebAssign likes that. Okay, and you want to do it that way because, like on the exam, it'll want that. I mean, it's still okay. It's still okay. It isn't like letting K equals 30 is wrong. It's just this value here that I circled in red is a smaller K value, but use K equals, like in this case, 30, and then compute your error bound. You want your error bound to be less than 1/10,000th. So, no, I'm sorry. You want the error of your trapezoidal approximation, okay, which would be the difference of the trapezoidal approximation and the true value of the integral. You want that error to be less than 1/10,000th. Well, by having your error bound less than 1/10,000th, that assures that your error will be less than 1/10,000th. So again, here we go again. We have an inequality to solve for n. Please let me know if you have any questions before we go to the next page.
So I have a quick question just to clarify. So when we graph double prime the function, the second derivative function, we're going to choose the x value that corresponds with the maximum, right?
That's correct. But it doesn't work for this problem, because if it did work, we would have just substituted x equals 1 in the second derivative and then use that for K. But in this problem, what WebAssign wants is it wants you to say, hey, sines and cosines, they're never more than 1, so replace them with 1s. And, and then you get K equals 30. It's only for sines and cosine functions, Nathan, that WebAssign wants you to do that. Like the previous example we did with the e to the 1 over x power, the second derivative there, we did say, hey, the function's maximized at x equals 1. So, and but we got a nice value of 3 times e, you see. So I know it's kind of, I think it has to do with the programming too, it makes the programming easier for checking and so forth. But yeah, that's right. That's right. All right. Are there any other good questions? The reason Marcus, we use the Marcus is asking why do we use the absolute value of the second derivative? Marcus, you'll have to go to graduate school to find that, to find out why, because it's proven, but I don't think they prove it in our textbook. But you have to take a course in numerical analysis to see why that's true. It's a very good question. Let me just look here just to double check. Yeah, I see they give the error-bound formulas in the textbook, section 5.9, but they don't like justify them. So Marcus, how about it? You think you'll take numerical analysis maybe to see why those error bounds are true? What do you think? Thumbs up, thumbs down, or no, thank you. Okay. Okay, so class, here's our inequality. We have to solve it for n. Okay, so next page, here's the inequality. I go through solving for n, and it turns out that n is greater than or equal to 158.114. So therefore, you would need 159 subintervals to ensure that the trapezoidal rule approximation would approximate our definite integral to within 1/10,000th. All right, let me give you a moment to copy that down, and please ask if you have any questions. Okay, and I won't close the page out yet, but are there any questions? Who's feeling okay? Who's feeling okay? I know you're probably maybe not completely comfortable, but who's like, I'm okay, I'm good. Who's somewhat comfortable? All right, Renat is okay, and Sean. Hold on here, and Abadara. Okay, good. All right. Well, on that note, let me stop the recording.